Today I'll be solving a question from the HSC Maths Extension 2 sample exam paper, and question 11C, where we have an integral involving partial fractions. The first part is to find numbers a, b, and c that satisfy this rational function equals decomposing into partial fractions. Okay, so for this one we can expand the right hand side. So we have a of x squared plus 2 plus bx plus c and x minus 3 and x minus 3 x squared plus 2. Okay, so this is just putting the fraction under a common denominator, and now we can collect like terms and we get a plus b x squared plus, we have minus 3b plus cx, and we also have minus 3c divided by minus 3c plus 2a and x minus 3 x squared plus 2. Alright, now we have to solve for a, b, and c. Okay, so by comparing coefficients we have a plus b equals 1, minus 3b plus c equals 8, minus 3c plus 2a equals 11. Okay, so got three equations. So we can write b as equal to 1 minus a, which means here we have 3 of 1 minus a plus c equals 8. And this means 3a minus 3 plus c equals 8. This means 3a plus c equals 11. Okay, now by combining these two facts, minus 3c plus 2a equals 11 and 3a plus c equals 11, we can multiply this equation by 3 to cancel out the c, and now add these two equations to get 11a equals 33 plus 11 equals 44, so a is equal to 4. And now c is equal to 11 minus 3 times a, which is 11 minus 3 times 4, which is negative 1. So, and now finally b is equal to 1 minus a, which is equal to 1 minus 4 equals minus 3. So now the partial fraction will be x squared plus 8x plus 11 over x minus 3 x squared plus 2 is equal to, we have a is 4 over x minus 3 plus b is minus 3x plus minus 1 is c over x squared plus 2. Okay, so that is the partial fraction decomposition. Alright, now we have to find the indefinite integral. So what we can do is, the indefinite integral, we can use our partial fraction decomposition. Now we can just add two integrals. We have the integral of 4 over x plus 3 plus the integral of minus 3x plus 1, minus 1 over x squared plus 2 dx. Okay, this we'll have 4 of ln of x minus 3, and can put a minus sign here and put 3x plus 1 over x squared plus 2 dx. Okay, now let's say we did a u substitution where we have x squared plus 2 in the denominator. What if we did u equals x squared plus 2 and du equals 2x dx? So then we would have the integral of, for example, the integral of 2x dx over x squared plus 2 would be equal to ln x squared plus 2 plus c. And this is kind of close to this integral, but we have a 3x instead of a 2x, so we could put 3 over 2 as a factor in front. And this is now equal to the integral of 3x dx. And this is equal to 3 over 2 ln x squared plus 2 plus c. And now this means we can put the integral equals 4 ln x minus 3 minus the integral of 3x over x squared plus 2 dx minus the integral of 1 over x squared plus 2 dx. And this is 4 ln x minus 3 minus 3 over 2 ln x squared plus 2 minus the integral of 1 over x squared plus 2 dx. Okay, now this is a standard integral where we have 1 over x squared plus something squared, which is root 2 squared, and this has an integral of, using the standard table of integrals, is 1 over root 2 tan inverse x over root 2 plus c. Okay, so this means we can finally write the entire integral as 4 ln of x minus 3 minus 3 ln x squared plus 2 minus 1 over root 2 tan inverse x over root 2 plus c. And in fact we can remove the absolute values here, because x squared plus 2 is always positive, because x squared is always at least 0. So we end up with this as our final answer to this integral, using this integral of the rational function using partial fractions. Okay, so just to recap, we first found ABC that satisfied that to create this rational function in terms of by having just the x minus 3 and x squared plus 2 in the denominator. And after we solve simultaneous equations to get the partial fractions, now we can compute the integral of this rational function, and we've split it up into several smaller integrals, and we've used some of the standard table of integrals to find the integral of 1 over x squared plus 2, and we've got our final answer over here. Okay, so hope you enjoyed this video. Thanks for watching, and I'll see you next time.